places to ship from and places to ship to is very large. What's happening there? Well, you know, you still have to do all those constraints. There is no other way around it. We also looked at a special case of a transportation, of a mean cost network flow, which we call the transportation problem. And I'll kind of flick through this stuff. The transportation problem is the version of mean cost flow where we only have two types of nodes, two classes of nodes. First class is the supply, the second class is the demand. There is nothing otherwise. And in that case, the problem is a bit simpler, because you've got a bipartite graph. On one side, you've got all the supplies, on the other side, all the demands, and your shipment routes are very simple. It's just one arc. And hence, the formulation is a little simpler. We separate the supply and the demand, and we have the constraints separately for all the supply points and separately for all the demand points. We also saw a bit of a small example right here of a transportation problem. That was the problem of supplying electricity from 3 plants to 4 cities. We spoke first about the mean cost network flow and the transportation being a balanced problem, where the total supply in the system is equal to total demand in the system. Further, we went on saying that it is possible to have a case where things are unbalanced, where you have either excessive supply or you have a shortage, where the supply is smaller than the demand. And we spoke about ways of handling that. In other words, there are ways of reformulating the problem so we still bring it to the classical version. And the reason for bringing everything to classical version is because algorithms for classical problem work very well, very fast, and you know, they do it like that. Once you have a little imbalance, then you may encounter certain problems. I also have to mention the following, that contemporary algorithms and contemporary software, everything that is available now, almost everything that is available now, is fairly sophisticated and smart. And every time you input a problem into a solver of any kind, be it Cplex or other, you know, Gurobi, there is a number of things. I'll actually probably mention those so that you have them in your notes in case you decide to go deeper into this story. So on the market, there are 3 main solvers that exist for linear programs, quadratic programs, integer programs, and things like around them. I was going to say number 1, but it's not really number 1. It's just one off, right? So one off is called Cplex. Another one is called Gurobi. And the third one is called Express. These are the 3 main solvers that exist on the market. These are commercial solvers. They are the fastest solvers that are available on the planet. They compete constantly with each other, and one version of one of these will be better in a particular class of problems, then they will be slightly slower in the other class of problems, so they're constantly making things very sophisticated and very fast. The sophistication comes in the following way regarding our problems, that once you input the problem, be it balanced or unbalanced or some sort of networking structure, the system recognizes the networking structure in your model and tries to take advantage of it. And they're trying to use specifically designed algorithms for these problems to solve it a bit faster. Whether it is helpful or not depends on the case, but very often it is helpful. Which brings us to the following point, that often the formulation of the transportation problem, let me sort of come back here, right, where we have, for example, we have a transportation problem and we have these equalities here. These equalities only work if we have a balanced problem, obviously. If the problem is unbalanced, having these equalities here is not going to work because all conditions are not going to be satisfied. So in the unbalanced case, for example, in the case where I have a excessive supply, I have too much supply, my demand is smaller. Right? The total demand is smaller than the total supply. What I can do is I can the equality sign with the inequality. And I can have the constraint being my xij, where the j's are going from 1 to whatever n, being less or equal to si instead of the equality sign. That's another way of handling unbalancing instead of putting the dummy node. Yesterday we spoke about introducing an additional node, putting the arcs. We spoke about what the costs on those arcs mean and what kind of interpretation they have. One of the ways to do it is just doing this. The second constraint would be your typical equal to the, what is it, j. Right, something like that. This is the case where my total supply is greater than the total demand. Right? Obviously, in a similar fashion, in the case where I have the total supply being strictly less than the total demand, right? I can do a similar story, my xij being less or equal to the respective demand. I from 1 to m. Am I doing the right thing? Well, if I messed up something with the indices, you understand what I mean. Like that. The problem with introducing the inequality instead of doing the balancing is that now you're essentially, it's like saying that my undersupply and or excessive supply, they don't really mean much. It doesn't cost me anything to have an excessive supply and keep it somewhere, or undersupply some of the points, right? So it's like having a zero cost on those arcs. That's what's happening if you're introducing this. So whether you want to work with one or the other depends on the application, depends on the context, depends on the problem that you're working with. Often you have to be very careful and you have to specify that undersupply, where you supply less than it's demanded, costs some money, and therefore you have to put it into the objective, and you have to, right, and we spoke about it yesterday about the priorities and things like that. So these type of formulations, they assume that everything has the same priority and it doesn't cost anything and doesn't affect its total cost. Keep that in mind. Today I want us to continue talking about these special cases, and the second or the next special case that I want to talk about is the so-called assignment problem. It's also in your slide, in your handouts. The assignment problem, as it says here, and it will become obvious very quickly, is also a special case of a mean cost flow, and it is also a special case of the transportation. So now we are making an extra restriction to the transportation problem. What we are doing is this: we're saying that the number of suppliers or supply points is exactly equal to the number of demand points or number of consuming points, right? So in our bipartite graph, the number of nodes on each side will have to be exactly the same. I don't know, I'll put it somewhere here. Right? For example, I'll have to have 4 on one side and 4 on the other. And this will be the demand. This type of problem is also restricted to the following. It says here that each supplier has just a unit of supply. One. Can supply only one of whatever you can imagine. And each consumer or each demand point has a demand equal to 1. Right? Which has a very interesting interpretation. Obviously, from the transportation point of view, it's kind of silly. But interpretations are quite interesting. And here is an interesting interpretation. There is more than one. I'm giving you one of the interpretation. It's a classical thing. It says that what we are dealing with is essentially n persons and n different projects or jobs. And the task is to assign a different person to one of the projects. So for each project, I want to assign a person who will be doing that job or doing that project, and hence assignment problem. Right? And I want to do it in such a way that the total cost of doing this, performing these jobs, tasks, projects, is minimized. Okay? What I'll need for this problem is the cost of person I performing a task J. That Cij as a cost is there. My objective function looks exactly the same as it does in the classical transportation problem. What will change is the following. My constraints are now, on the right hand side, they have ones, because my total demand at each point, or demand at each point is 1, supply at each point is 1. So these things get simplified. I also have a condition of non-negativity, but as a result of a unit of supply at each point and unit of demand on each point, my variables, which represent the amount of flow, they will now, the interpretation of the variable is who is assigned to what. All right? So when the variables are only going to take two values, either 0 or 1. No matter what I do, if I have this condition, supplies are 1s, demands are 1s, all my flows will be either 0 or 1, with the interpretation that if it's a 1, it means that person I is assigned to project J. If it's a 0, it means that it's not assigned to that specific project. You understand what I mean? Is everything clear? We will look at an example of the assignment problem which I have here. And the example is the following. I've got 4 machines and I've got 4 jobs. I have a company that has this problem, and what it wants to do is assign the jobs to machines so that they can be completed in parallel. And the problem here is this. Different machines need different amount of time to be set up to perform different jobs. So my cost now is expressed as the number of hours that will take to set up machine number 1 to perform job number 1. Right, in this case it's 14 hours. Machine number 1 is more suitable to performing job number 2, and hence the setup time is smaller, 5 hours only, and so on. So that's the interpretation. Once I formulate this problem and solve it, I will have the optimal allocation of the machines to jobs, or jobs to machines, whatever you like, so that the overall setup time is minimized. Okay? So let's maybe write it out so that we are again a little bit more in sync. And then after this, we will try and solve this thing on the computer. That'll be fun. So, I should probably keep it. Some of this stuff. Alright. So since we are talking about a special case of a transportation and a special case of a mean cost flow, what I want to do is do the graph as well, like I do it usually, because then things become very clear. I mean, it's easy to formulate once I've got a pictorial representation of my story. So let's do it. I will use a green here to redo that. So these will be my machines. 1, 2, 3, and a 4. And these will be my jobs. 1, 2, 3, and a 4. And now, like before, the labeling of nodes is very arbitrary. I just like it like that. It makes me feel better. That's why I do it like this. And my conditions here tell me that I have setup costs for every pair of job, or for every job machine pair. Therefore, I can perform any job on any of the machines, which in transportation terms means that I have an arc coming from every job, every machine into every job, like that. if I want to be very pedantic about my graphical representation, I can even say things like this. S1 is equal to 1, S2 is equal to 1, S3 is equal to 1, to 1. And here I will do D1, 1, D2, 1, D3, 1, and D4, 1. Like that. I can even go further and start putting, we haven't done it before, but I can even on the graph put all my costs. So for each specific arc, what I can do is, for example, for arc 4, the cost of machine 4 being performed, being set up for job number 4 is a 10, right? So I can use a 10 here as a label on the arc. People do it very often. I'm not going to do it on this whole thing because it's going to become very messy and it's going to be very difficult to read. Instead, I'll just keep that matrix and it will be easier to work with. Now, the formulation is very similar to what we've done before. The only difference is that all the right-hand sides of my constraints are now ones. And I can even use a bit of this story already written out. And maybe I will do one constraint. Let me do one constraint completely. So I'll say subject 2, and my first constraint is the constraint for machine 1. It's going to be x11 plus x12 plus x13 plus x14. It has to be equal to 1. Okay. Similarly to this for machine number, I can even make a label here, but this is machine 1. For machine number 2, I'll do a similar thing, and so on. Alright, so it's going to be, let me do it like that. It's the sum of x2j, where j is from 1 to 4, and it has to be equal to 1. And then further, it's the sum of x3j, where j is from 1 to 4. This is equal to 1. This is machine 3. Similar for machine 4. Something like that. Similar story with the demands. I will look at it and say, wonderful, for the, let me do it like that. This will be a jobs, right? So job 1, the constraint is the sum of x I1, I going from 1 to 4 is equal to 1. And so on. Obviously, I will need my non-negativity for all ij's, and that's it. Oh, objective. The objective is to minimize the cost, the total cost. And as before, it's exactly the same objective as before. I have my costs. So for example, here it's 14 times x11 plus 5 times x12 plus, and all the way to x43 times whatever the cost there is, 6 plus the 10 times x44. That's my formulation. I want to bring your attention to the following, that from the purely sort of, from this point of view, I formulate there is nothing particularly fascinating about it. It's all very clean and very trivial and very simple. What's important is to follow the network flow formulation. And because of the integer right-hand sides of all my constraints, what I will end up having is always integer solutions. So that integrality property that we spoke of yesterday is playing a big role here. Because if it wasn't for that integrality, then I could have gotten solutions like this. Let's say x11 like a 0.7 and the x12 is like a 0.3. And from my point of view, from what I'm trying to do, the x being 0.7 is nonsense. It's stupid, right? But the integrality guarantees that my x, one of the x's will be 1 for this node, one of the flows will be 1, the others will be 0. Guaranteed, you don't have to worry about it. Which means that I can use a simple simplex algorithm for linear programs, always guaranteed to get an integer solution, very fast, very efficient, no matter how big the problem is. Okay? And I will give you another sort of historical note that a person who stands behind a lot of the developments in the linear programming, who is considered to be the founding father of all that stuff, whose name is George Tanzic, who was working at Stanford during the Second World War, slightly before and some years after, who is also considered to be the father of the simplex algorithm. The problem he was working on, and how he developed that algorithm and methodology for solving LPs, is solving this problem. He was trying to do it by hand, right? No computers, nothing. And when the problem was 10 by 10, things were quite all right. But, well, maybe even less than that. I mean, 8 by 8 was something. But then as soon as they go into higher dimension, it was absolutely impossible to solve it by hand using just simple methods. Anyway, this assignment problem has this interesting history, and it can be used for many other applications, not only simple assigning one to the other. Everything that has a particularly sort of, that you can formulate in this sense, you can use this problem for. Maybe let's try and solve it using the machine. What do you say? Should we try? All right. I have the following here. And I will actually... So, please get to the computers and open an Excel and open an empty spreadsheet, whatever. What I want you to do is input the data. This is just the cost matrix for 4 machines, 4 jobs. I kind of decided to make it a little nicer so that it's easy to see. But you can do it in any way you want. Just make sure that it's a matrix of this, it's the same shape as we have on the slide. Do that, and then once you've done that, just make a copy of it right next to it, and I'll tell you what to do next. Okay? So, if you have that little screen popped up, just close it, and we will bring it back up again.
Do you may use any numbers?
No, you need to use those specific numbers that are in the slide. You have the data in your handouts, right? I'm not trying to make your life complicated. So in the handout, there is an assignment problem example, and you should use those numbers. The matrix is 4 by 4, columns are jobs, rows are machines, and the constants are given. Josh, you need help? Right. Do you have the handout from yesterday? So once you've done that little matrix 4 by 4,
What do you want? Copy?
Then copy and paste it right next to it, right? Or in my case, one starts from A to column E, and then from G to K, I've got it's copied. And once you've copied that, you can delete all the numbers, make it either empty cells or zeros, it doesn't matter. In the copy, the original should remain there. We will need the original for the cost function, for the objective function, and the copy we will use as the cells for variables.
Yes. But need zeros.
We need empty spaces or zeros?
Doesn't matter. Excel these days is smart enough to understand that both zero and empty space are practically the same thing. Once you've done that, we are now ready to do both constraints and the objective. Right? So let's start with the constraints. We will start with the constraints for machines, which in case of this graph means the constraints for these four nodes. The constraints are very simple. It's just the sum of the variables has to be equal to 1. Right? So that's what I'm doing. In the column L right next to this matrix, I have a sum of the associated cells. Right? So I'm summing. You can do one plus the other plus the other plus the other. It's going to take a long time. It's easier to just say it's the sum, and then you indicate which cells. I mean, you can do it like that. Check this out. I'll start from the beginning. So I say equals to, and then I go sum, open the brackets, and then simply drag through all the cells that want to be in the sum, and then I close the brackets.
They need to put sumo.
Ah, holy mackerel, I forgot that you guys have it in a different language. I apologize. What's that?
Sumo.
Okay, so what you need to write is
What? Sumo.
No,
Oh
but
no,
in
we
like
Ukraine.
that?
No.
Like that?
Yeah.
I'm sorry, I didn't think about that. So, in the Cyrillic, if you have the non-English version, type CYMM, but like sumu. And then you open.
Yeah. And now put.
Yeah, I apologize. That's a bit annoying. But instead of the plus, you have to put
Знаешь, я бы могла нажать разом.
Really? It doesn't take the English? Yeah, and then just drag through these four cells. There you go. And then
Help you?
but I want you to have this.
I know.
Are we? Is it happening?
Written in Cyrillic, not in.
Yeah. Should be written in Cyrillic alphabet. We have a few people walking around helping out.
No, it's not so heavy. Just
Working.
So yeah, once you've done it for the first thing, for the first cell, what you can do is simply, when you highlight the cell, like this, you bring this little cross to the bottom right corner. It turns into a black cross. You hold it and drag it down like that across all four cells, and it will do the same formula only for the associated row. You can then click on it to verify that you've done the right thing.
What I miss? Instruction.
Once you've done that, I want you to do a very similar thing only for the jobs themselves. So now at the bottom of each column of the matrix of variables, you do a similar formula only for the column cells. And Right, so these
Yes.
cells at the
Okay.
bottom, they also have the formula that is the sum
What?
of the things here. And I actually insist on you doing it precisely in this way because there is a reason for it. It will make things very easy to see and simple to refer. Don't place these sums elsewhere, just put them where I do. Once you've done that, then both here and here you should put in the next, I mean in this case in the row under, you put the sign of the constraint. In our case the constraints all have the equal sign. So you simply as a symbol put the equal sign all the way here. Again, it's for your sort of, you can see it's good for you. Right? Similarly here. And the next cell after it, you put the right-hand side of that constraint. In our case, all the right-hand sides are ones. Okay?
What?
Would be equal sign and one.
Equals, ones, and similar thing on the left, on the right from the matrix. Okay? This stuff over here.
You can drag again.
Same thing. Equal sign, and oh, maybe I can make it bigger so that you can see better. There you go. Oops. That's it. Right? Formulas here equal ones. Formulas equal and ones. Everybody good so far? Can we turn on the AC? Because people are melting. Is it possible to switch it on? Maybe. Yeah, if you can close it. All right. Everybody good so far? Wonderful. Now, the next thing that I want you to do is to input the objective function. That's the most difficult task here. The task is difficult for two reasons. First, there is a lot of things, there is a lot of symbols there. And second, I don't know any better way of doing it. I'm sure there is some other ways of doing it, but I don't really use Excel very much. So I do it the way I can. So I do it like that. I say, take cell job multiplied by cell here with the cost plus the next cell here multiplied by the associated cell. So I essentially do it all like that.
But it's not easier to use the sum product function.
Probably yes, but I don't know how to use those things. If you guys can, do the best way you can. But the idea is that you write out all of this somehow in one cell, and next to that cell you put a word objective so that you know what this cell stands for. Right? So you go x equal sign and then whatever formula to make sure that the objective function is there. In my case, I just do it, you know, in a bulletproof way.
Maybe we put some numbers.
No, do not do the numbers. If you start putting numbers instead of the reference to a cell, then you cannot change the cost without going, and you'll mess up everything. Do the reference. As I said, I'm sure there are easier ways of dealing with this stuff in Excel, but I just don't know.
What do you want?
I just want. It's okay.
Like this. Summa proizvod. And select.
That means what?
Some product. And then you just select erase.
Yeah. You know, fast way?
like to help them?
No Pascal?
I ask you.
Help them.
I cannot help them anymore. I don't know how.
I would like to help
You can help? Alright, you can do that. Ah, interesting.
So you actually managed to do it fast way?
I have some product, I have English in the variants.
Is that the sub-product? This how we see in the sub-product?
Yeah, that's a sub-product. The sub-product is called this way, and then you have two parameters there. One of them is first matrix. You select the whole matrix, and then after comma you do the second matrix, and it should work. But as I said, I am, not Excel person. Let's check it out. Maybe I'll.
Now it's changed.
3 times. First is English, second Ukrainian, third is Russian. Some product.
Yeah, we'll see. If it works, it works. All right. Ready? No. No. All right. Let's wait.
Everything is all.
For you it would be nicer just to click each of them.
No, it's not. I'll just put comma.
But here is dot and comma. Oh, just try it. Dot and comma, you see?
Надо английский писать.
Что, да?
Это нам на алфавитиcal order.
So, are we there? Have we done the objective function?
No, wait a second.
Wait.
I've been waiting for some time.
Can you show the second?
The second one looks like this. It's the
It's done.
sum product
We will check by adding some values
and
here and
two arrays.
it should calculate just
Second version.
but one yes,
Can you show?
Zoom, pro
You guys are good? Are we're done? Nice? No. Still no. Do the sum product.
Select the first yes.
My method is very slow.
Take the sum with dot and comma.
Right.
I don't know where it is in English.
Second.
You get the
yes.
check if it works.
One. Work like a clock.
Yes.
We'll wait for another minute and then we'll have to move on.
Not the same version of Excel. So the solver will be somewhere.
Yeah, it looks very similar. So, yeah, I know it's always this Excel bloody. It's always different. But solver is very similar. So we will try and find common ground here. So are we, ladies and gentlemen, can we move on?
Yeah.
All right, we are moving on. Now we've set up the problem so that we can now call the user interface of the Excel solver, which is an add-on to Microsoft Excel. It's the thing that has a few algorithms built in and will help us solve the linear programs. In the English version of or English version of Excel, this thing is located in Tools. In your case, it will be in the same position, only that it's going to be called something else.
Yes, service.
Service.
Service. Next one.
Alright, so you guys need to find, I know it's kind of funny, but
One more.
yeah.
This one. Select.
You need to find a menu item that is called like this. First, in the top menu, you will find something called service, which is somewhat loosely translatable into tools, but not really. It's more like a service. Right? Then you click on it, it brings down all this stuff, and somewhere in the middle, you will find called поиск решения. Like that. Okay? You're looking for this thing. Everybody got that? Once you've got the interface, I'll show you what it looks like.
Yeah.
It looks like this. Or similar.
Yeah, except we don't have the data yet.
Only that you don't have anything in these cells, right? I'm going to delete mine and we will populate them together. And I'll delete this. So you should have something like this popping up. This is the interface of Solver. You can see that at the top here is where you will be selecting the cell for the objective function, where you inputted that objective function, either the sum product or that long story that I've done. Right? So what we will do is we'll click here, and we will locate the cell, select it, like that.
What cell?
One cell, the objective.
What? Какая?
The one where you put the objective, I have no idea. You selected it, right? In my case, it's the cell right here, with the objective function. It's where the formula is. Okay, so I put it up there. Now I've got to select what is the sense of my objective. Am I trying to maximize that cell? Am I trying to minimize it? Or am I trying to bring it to a specific value? There are cases where I want to bring it to a specific value. That's a different story. It's the whole summer school in its own. So we will select the minimization because we are interested in minimizing the value of that cell. Okay? So in Ukrainian or Russian version, it's going to be it's going to be not the top one, but the one under. You select that. Then the next long thing here is where you tell the computer which cells represent the variables. So in our case, the variables are a matrix that you've populated with zeros. This thing here. Make sure you do not select the cells where you put formulas, right? Only the 4x4. You've selected that. All right. Now we can add the constraints. Right? So far we've told the machine what's the objective, what's the sense of optimization that we're trying to perform, what are the variables. We need to add constraints. To add the constraints, you click on the button add, or in Ukrainian version, it's also the top button, it's called дають. The top button on the right hand side. Okay? You click. Right?
Yes.
You click on that button. So you've got a small dialogue. Now, in this small dialogue, this is where we will see that the positioning of our formulas for the constraints is going to help us out, right? So look what I do. I will select this row that represents 4 constraints for 4 jobs, like that. Once I've selected them, it comes into here, into the cell reference. Then I simply say that I want it to be equal to
4.
and all 4 of them, yeah. And then I select 4 ones or 4 right-hand sides, and that's my constraint. And then I click the button add, and it gets added into the system's set of constraints. So in other words, instead of doing it one by one, I can do them in the whole sets. Right? And that's why I want to position my whole problem in this way, because it's easy to select all the variables in one go.
Next step.
Next step, I'll do this for these cells, which represent for the ones that represent the constraints for machines. I select them in a similar way. I will set the sense for the constraint. I want it to be the equality constraint, and I'll select the right-hand sides. Now I can click a button OK, and once I've clicked OK, I'll get back to this interface, to this menu, where I've got 2 sets of constraints here. I've got the set of variables. I am minimizing, and I've got the cell for objects. You got all of that? All right. Now, there are 2 things that I want to do now. One of them is in this drop menu. I want to select the simplex LP, because what I'm interested in solving a linear program. When it comes to your version, you will need to click on
Parameters.
So in your version, you click on the button parameters or parametry. It's the button looks like this. Right? You clicked on that button, and on the left-hand side, оценки линейная. No, actually, all right. I'll try to maybe somehow I need to show you what to do, and this becomes annoying. Maybe I'll bring up this computer. No, I can't. When you
Может твой компьютер подключить?
Не на английском.
Проектор.
На английском. You need. Лінійний, окей, лінійний, оцінки лінійні.
Yeah, I'm thinking what's the best way of doing it. So what you...
А нужно по линейной по умолчанию стоят.
It's good, yes, and
Линейные должны стоять и не отрицательные значения. So, I'll draw it.
Good, не отрицательно. Yes, не отрицательно.
So once you push the button called parametry, you will get a menu where it will be sort of separated into several things. There is a whole bunch of text and the boxes with some tolerance parameters and stuff like that. Then in the middle here, you have several tick boxes that you can put a flag on. So you need to flag the ones that are on the left-hand side, not the very bottom ones, because there are some things here as well. But in the middle, there are two ticks that you need to. The first tick is indicating that we want to use a linear model. In my case, I just selected here. The second tick indicates that we want a non-negative values for the variables.
Да.
Right? Once we've done that, it means the non-negative values of the variables takes care of this constraint. So we don't need to add this constraint separately. If you are unsure, you can add this constraint separately by doing similar thing that we've done.
Linear, non-negative and linear model.
Linear model, non-negative values.
Не отрицательное значение.
Exactly. In my case, it looks a little different, and you know, what can I say? Microsoft. Once you've done that, then there should be something like an OK where you get back to this menu here, to this interface here. Right? Once you've got there, what you need to do is to click the button Solve. It should be located at the bottom here. No?
No.
At the top?
Выполнить.
Yeah, at the top there is a button called Выполнить. Right? At the top, the button is like that.
What?
15 is the price
What price?
of the assignment, meeting the jobs.
You need to find this button. Once you found this button, push it and let it go. And you will get this. This interface or this menu says that the solver has found a solution, and it's asking you several things. First, it says that I can either keep the solver solution, like this first element here, keep the solver solution in the cells that we were trying to optimize. Right? The other option is to restore to the original values. Our original values were zeros or nothing, depending on how you've done it. Make sure you have it indicated at the top here. The first, you select the first one. Right next to it is the number of reports that you can generate. For the problems like this, we usually are fine with the first report. You just have to click your mouse on the first one, so it's highlighted. The first is the answer. Just the values of the variables and the final value of the objective. The other ones are the sensitivity and the limits. Because we have a very short time talking about sensitivity, I mean, it's going to take a long time, so don't worry about it anymore. Just select the answer and click OK. What's it called there? Is it OK? Alright. And you will get
In the bottom.
at the bottom right hand side of that should be a button that says OK.
Here is it.
What you will have now is a second tab generated. You click, you find that second tab. This tab is called Answer Report, and in your case it will be Answer Report 1. It should look like this. Right? Once you've clicked OK, the report will be generated and it will come up as the again in the language that you have there, it's called short or horizontal, something like that. You bring it up, and once you brought it up, I'll say a few words what these things show. First of all, there is a lot of nonsense about what was used and who owes the rights, and then there is a bit more that we use the simplex, certain number of time that was spent, certain number of seconds that was spent generating this solution, number of iterations of the simplex algorithm. Anyway, all sorts of technical information. What you're interested in is things starting from here. The first bit is gives you the value of the object. So your minimum cost is equal to 15, whatever the units were when you were plugging things in. Right? So your objective is 15. Then further, you get the actual variables, the values of the variables. Right? And in the way I set it up, it's easy to read now because the variables are machine 1, job 1, machine 1, job 2, and so on. This is the first column is the original values, and the second column gives you the final values or the optimal values of these variables. They are all here. Further, the next column indicates whether they are continuous variables or integer or any other kind. In our case, it's continuous. Right? Another thing you can do in order to see what the results actually are is go back to your assignment to this. I'll make it a bit smaller. Go back to your setup of the problem and you will see that where you have the value of the objective, it gives you that 15. And then here where we had the variables, now you see where the ones are, where the zeros are. And it's very clear, and you can read it in the following way. Machine 1 will get job 2, machine 2 will get job 4, machine 3 will get job 3, and machine 4 will get job 1. That's your interpretation of the solution. Okay? That's how you read it. If you have a larger problem, and you can manage it with Excel in this way, fine, do it. But problems over, if you can have 10,000 variables, doing it in Excel is really painful. So for that, people do not use Excel, they use other languages, modeling languages like MPL. They also use, there is a number of languages that are specifically for modeling purposes. And another one is called OPL. This is something that comes with Simplex. You can also do it in Python, and you can do it in other languages. All the solvers that exist, all the ones that I indicated, they have interface with Python, with MPL, they have interface with MATLAB. You can do it through MATLAB, you can do it through other languages. But the main point is that once you've got big problems, you need special data structures to handle that stuff. You can't really do it with a matrix of this sort. You have to be much more selective in the way you introduce variables, right? Because I've had experience with certain, also similar to this, assignment problems where not everything would be assigned to everywhere, and therefore the number of variables that you need to deal with is much smaller than this type of setups would indicate. And if you are careful in your modeling and in the choice of the language for the actual modeling, then the number of variables and the size of the problem can be reduced significantly. I had things like, from 4 million variables go down to 1.5 million, which is a big difference, and allows you to actually solve the problem as opposed to just stare at the computer for hours and hours without. So it's very important. the language considerations, they become important when you start dealing with large problems. If the problems are smallish, where you've got up to 100 machines, jobs, and whatever, matrix 100 by 100, you can handle it no problem using Excel. Okay? So just keep that in mind. Questions?
Yes, what kind of a problem consists of 4 million variables?
There are lots of problems that can have that many, maybe even more. And these are the problems where imagine the following situation. You've got about 30,000 different objects that need to be assigned to about 1,500 different bins, right? Let's call them bins, like boxes. I'm not gonna go into the details of the actual application, why it was done, why I was doing it. That's a different story. But imagine you have 30,000 objects. You need to assign them to about 1,500 bins, and the assignments have lots of different restrictions. Certain objects can be assigned only to a certain number of bins, and so on. But it has to be done in such a way that you minimize some sort of an objective. The objective was also a complicated function, big, messy thing, but in order to handle the restrictions on the assignments, because some objects could be split into halves, or they could be split into thirds, into 3 pieces. And those pieces could be assigned to different bins. So in order to handle all of that, if you do it in a very crude way, you may end up with about 4 million variables. And if you do it carefully and you start sort of taking care of what variables you introduce, which things shouldn't be there at all, and the choice of language in that case made a big difference, and the choice of the objects that represent the whole problem made a big difference and reduced the problem size.
Can you just shortly say what was the application in real work?
The application had to do with the following. In academia, universities in the Western world specifically get evaluated according to their performance of the academics. The performance is measured by how many articles people publish within a certain period of time. And each article is considered to be better or worse depending on which journal it goes in, and also depending on how many citations it gets. Now, in Australia, there was an exercise where the universities had to present a report on the performance of different departments. And the report had to consist of the averages on the citations by different areas. And the averages are not just the average on the citations, but it is also weighted by the citation average of the world. Right? It's a very massive thing. And there is also a measure that has something to do with what's the average citation rating of a journal where that paper is published. And anyway. So the whole problem there is the following: that different papers and different journals, they can be allocated or can be considered. Any journal, or many journals, I'll rephrase it, many journals, they can be considered as a journal of several different fields. For example, there are very important journal, very popular journals called Biometrica. It's a very fancy journal. Biometrica publishes papers that have to do with biology. It also publishes stuff that has to do with statistics, because to do stuff with biology you need methods, and methods are statistical, also optimization is there, computer science. Now, if you publish a paper in Biometrica but you are a member of a computer science department, then things become, well, I mean, do you consider it to be a paper in biology, or is it a paper in computer science, and so on. And that becomes a very big and complicated problem. So, in a few words, that's what it is.
Okay, thank you.
All right, so any other questions? Let's have a short break because some administration has to be performed on you. Don't move. And we will reconvene in about 5 or so minutes.